Hello, welcome to FlippedHarber for Algebra 2. In this video we're going to be talking about the natural base e. The objectives for this lesson are to learn how to write exponential functions using the natural base e, write logarithmic functions using the natural base e. We want to look at how to solve continuously compounded interest problems, and we want to take a look at solving a radioactive dating problem. Now, what the heck is e? Well, it's an irrational number that seems to show up a whole lot. When we say that a number is irrational, that means that the decimal continues on forever without repeating itself, without ending. Now, basically just like pi, it showed up so often that we decided to feed it and give it a name kind of like a stray cat. Now, what the heck is ln? You may have seen this on your calculator, you may have seen it in some books. ln is properly read the natural log. Now, e showed up so many times in logarithms that we gave it a special name here as well, the natural logarithm. A natural logarithm is basically a log base e. Remember that we can have a log base of almost anything we want. Any positive number that's not 1 can be a log base. In this case, it turns out that using a log base e was so common that we decided to call it the natural log, ln. Now, if you really think about this, it showed up so many times that we gave it its own notation to save 2 letters. How many times does something have to show up in order to give it a notation to save 2 letters? Now, let's take a look at a graph for e to the x. So this should look just like every other exponential function that you've looked at. It has this nice curve up. It goes through the y-axis at 1, just like every other exponential. It tapers off and approaches the x-axis as we go to the left. And as we go to the right, it points up. So again, it looks just like every other exponential function. This is just an e to the x instead of, say, 2 to the x or 5 to the x. Let's take a look at the graph for the function natural log of x. Again, this should look a lot like every other log base function that we've looked at. It goes through the x-axis at 1. It approaches the y-axis as we go to the left, but never actually crosses it. And when we go to the right, it continues up. So again, this looks a lot like every other log base function that we've seen. This is just a natural log, a log base e. Now, we see e and the natural log working together a lot in math. Maybe not so much here in Algebra 2, but we use it a lot in calculus and some higher level stuff. When we take the natural log of e, because the log base matches that number in there, the log base e, the natural log of e, is equal to 1. If we put a power on, oops, let me back up. If we put a power on that e, basically everything cancels but that power. When we see e with the natural log in the power, like we do over on the right, e to the natural log of 1, the e and the natural log cancel, it just equals 1. Or when we see a variable in there, or anything other than 1, the e and the natural log totally cancel each other out, and we're just left with that n. Now, in equations, we use e to get rid of natural logs. If I'm trying to solve for a function and I have a natural log in the way, try to solve an equation and I have a natural log in the way to get rid of that is to use an e. And vice versa, we use a natural log when we want to get rid of an e. Now, let's take a look at a continuous compounding situation. Now, we've talked about interest and compounding interest before. We have this equation, A equals, that is the amount equals the principal, 1 plus r over n, where r is our rate for our interest. N is the number of times that it's compounded. And then we have a power n times t. Again, n is the number of times that it's compounded, and t is the number of years. If we compound monthly, we just simply put a 12 in where that n is. If we compound weekly, we use 52 because there's 52 weeks in a year. If we compounded daily, we would put 365 because that's the number of times that we're compounding. So you can see a pattern here that as we get bigger and bigger and bigger, this fraction back there after the 1 actually gets smaller because that rate is getting divided by a bigger and bigger number. If we compound continuously, if we take this to the extreme, we go from compounding daily to compounding hourly to compounding minutely to compounding secondly. Eventually we get to this idea of continuous compounding. And you see that our equation changes a little bit. Instead of the 1 plus r over n, it's principal times e to the rt. A lot of times people read that as pert. It's an easy way to remember it. Now let's go ahead and take a look at a continuous compounding example. We want to know how much is a $1,000 investment worth after 2 years of continuous compounding with a rate of 2%. We're going to use our AE equals PE to the RT. We're going to plug that $1,000 in for our principal. That's the amount that we're investing into this. And our rate is 2%. So I want to enter that as a decimal, 0.02. And we're talking about doing this for 2 years, so we plug 2 in for our time as well. Plug that into a calculator, we get our amount is $1,040.81. Now this would be a really good time for you to stop this video. Try this out on your calculator. If you don't know how to use your calculator, you're not going to get these answers on the test. So take a minute, try this on your own and see if you get the same number. Alright, let's take a look at radioactive dating. Now when I talk about radioactive dating, not talking about this kind of dating at all. Okay? What we're talking about is using radioactive isotopes to figure out how old something is. We dig up a bone, we dig up, a clay pot from some archaeological site. We can use radioactive isotopes to figure out how old that sample is. Now the most common isotope that we use is carbon-14. A lot of times you've heard the term carbon-14 dating. What they do is they compare how much carbon-14 is left with how much carbon-14 the sample started with. And it turns out that all organic material, we're always taking in carbon-14, and we all contain carbon-14 pretty much in the same ratio. When we die, when we stop taking in food, the amount of this carbon-14 slowly goes away through radioactive decay, but the amount of other carbon stays put because it does not decay away. Other isotopes that we would use, potassium-40, rubidium-87, and others. It all depends on how old the sample is. If the sample is very, 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 very old, if we're talking about like a fossilized tree that might be, a couple million years old, carbon-14 is not going to work. All that carbon-14 has gone away. We have to use these other isotopes. Okay, so here's an equation that we need to use when we're using radioactive dating. We'll go over what each of these mean, but again, you see that E. So this is a great example of using this natural base E. N of T, this is not N times T, it's N of T, is how much isotope is remaining after time T. N naught, that's actually an N with a little 0 after it, is how much isotope we started with. Now this is usually a comparison between the N of T and the N naught. We usually don't know how much was in a sample, but we know it was a certain percentage. K is a constant that is different for every isotope. So we're going to have to calculate we're going to have to calculate K every time we do a problem so that we can plug it in. But in the real world, everybody that does this just knows what K to use for carbon-14 or potassium-40. Okay, so let's take a look at an example problem. It says a sample from a mammoth contains only 12% of the carbon-14 it originally contained. So we don't know how much it originally had, but we know a ratio, and we know that there's 12% of the carbon-14 remaining. Carbon-14 has a half-life of 5,730 years. We're going to use that number to find K. And it says use this information to find the age of the mammoth. All right, first of all, we have to find out what this K is so that we can plug it in order to find the age of the mammoth. Then we have to find out how old the sample is. It all starts with finding that K first. So let's go ahead and find K. Now, it all hinges on that half-life of 5,730 years. So you'll notice in my equation, I plugged in 1/2 for n of t, meaning that half of the carbon-14 is left after 1/2 life. So we plug in 1/2 for n of t. We plugged in 1 for n naught, meaning that whatever the sample was, the original amount is 100% or 1, and there's half of it left. We're going to have to solve for this K, so I'm going to take a natural log of both sides. Now, we're taking a natural log of both sides because we use natural logs to get rid of e's. That e just totally goes away with that natural log on the right-hand side, and we can solve for this K. So our K is about 0.0012. Okay, now this K is true for carbon-14 every time we use carbon-14. We just had to figure it out for this problem. If I was going to do another carbon-14 problem right after this, I would just use this K value. Now that we know K, we have to find out how old the sample is. We go ahead, use our equation again, and I know that there is 12% of the original amount. So for n of t, right here, I plugged in 0.12. That's 12% of my original amount. I don't actually know how much it started out with, but I know that there's 12% of it remaining. My n naughts just cancel out by division. So the n naughts just go away. Now I've got to get rid of that e. How do we get rid of that e? That's right, we use a natural log. So we take the natural log of both sides. That's going to totally cause this e and this natural log to cancel each other out. When that happens, we have the natural log of 0.12 equals negative 0.00012t. Again, that's that K value that I calculated. And then I divide it over. So I got a little bit of a typo here. Put another 0 in there. And we plug it into our calculator. Bada boom, bada bing. We find out that that mammoth is about 17,668 years old. Now, this is all an approximation. I only used a couple digits from that K, so I'd probably say that this mammoth was somewhere between 17,000 and 18,000 years old. This is a lot of digits to report. All right, so that's it. It's time for you to get to work. I'll see you in class, and I will see you online.